For this week, my plan is to finish chapter 4. Hopefully, start the next chapter. I have to decide which chapter I should cover after chapter 4. I'm still debating between 2 different chapters. And then for the assignments this week, you have lab number 5 report due this Friday. We'll be doing experiment on synchronous rectifier this week as the same topic of in chapter 4. And then homework number 6 also due this Friday, and then quiz number 6 also due this Friday. So lab number 5 report, homework number 6, quiz number 6, these are all the assignments for this week, and these are all due on Friday. All right. The quiz is going to cover chapter 4, which is synchronous rectifier, the topic that we're going to cover today. All right. And the midterm, I've graded those last weekend. Overall, the class did very well. Look at the average right there, it's 80%. It's pretty good, right? And unfortunately, I still have one student having a low score. Yeah, if you're the student, if you want to discuss the midterm with me, feel free to do so. Stop by during my office hours. I'll be more than happy to discuss. What needs to be done. To improve. The grade. Okay. Yeah, don't give up. Okay. This is week number 8 already, right? Just need to finish the rest of the assignments for this quarter, and then we still have final exam, right? So make sure you do well on those, and you'll be fine. Okay. Any questions on the midterm as well as on the weekly agenda? All right, and then a couple of you asked about EE433 that I'll be teaching next quarter. So I'm including the table of contents of the book for next quarter, and this should be also posted on Canvas in case you are interested in knowing what is covered in that class. So it's I would say this is 411 EE411B. Right? So it's the part of the power electronics sequence that we offer at Cal Poly. We have a total of 4 power electronics classes: 410, 411, 433, and 527. EE433 and EE527, they alternate every spring. So every other year they're being offered. So this year is the turn for EE433. Right, so next year's spring is going to be EE527. 433 is focusing on the magnetics of the power electronics, and I'm not going to go through this into details. You feel free to look through this table of content of the book that I put together for the class. Yeah, we'll go over the basic magnetics of the basic concepts of fundamentals of magnetics in inductors and transformers. So this is not like 335 or 402, okay? This is not electromagnetics, this is magnetic, and more specifically, high frequency magnetic design class. Right, so you look at the different aspects of magnetics, for example, hysteresis loss, Bohr loss, eddy current loss, skin effect, proximity effect, and so on and so forth. Okay? And then review on magnetic circuits, and then focusing on the loops, BH loops of different converters, right? And then we go into how to design a transformer for DC to DC converters, again, high frequency transformers, and the different methods on how to design transformers, right? And then the same thing for inductors, right? How different it is, designing transformers and inductors. That's chapter 5. And then ways to improve your design, how to optimize your designs. That's chapter 6 and so on, chapter 7 as well. Right, so that's basically what the class is all about. High frequency magnetic design. Right, this is a very rare class, by the way. You can check, Cal Poly is probably the only school in California that offers this class. And it's a very practical class. The content that I'm presenting is more practical rather than theoretical. Other schools, they may have something related to this, but they use more like computer-aided design, more like a mathematical, not mathematical, but finite element type of approach. Here I'm presenting the design based on practical approach, right? Not so much on relying on the computers, but more on hands-on method on how to design inductors and transformers. All right.
Do we learn about like actuators and stuff in that class, or like any like forces that magnets would like experience too, or?
No, I don't think we cover specific applications. This is strictly designing inductors and transformers. And depending on the application, the hope is that by knowing how to design inductors and transformers, then whatever applications you are in need of magnetics, then you can design the magnetics based on what's required from the applications. So yeah, does that answer your question?
Yeah.
So it's more like how do you design inductors, transformers based on requirements. All right. Yeah, I think that would be it. Let's see. Again, this is included in the weekly agenda that I've posted on the canvas. All right. Okay. Let's start our chapter 4. So chapter 4 is on synchronous rectification. We'll go over a diode that is being used for DC to DC converters. We're going to be looking more into the diodes actually, and then we'll look into different losses related to diode, just like we looked at losses for switches. Here we look at losses on the diode. And then by going through those losses, hopefully you understand why for some applications, maybe it is not beneficial to use diode, but rather use a different method to replace the diode. And one of the methods to replace the diode is to use another FET or another switch, solid state switch. And if that is the case, that's what's called, the method is called synchronous rectification, right? So if you hear the terms synchronous buck or synchronous boost, then that means you replace the diode with a FET or another switch. Okay, but let's go over this first. Let's go over the basic concepts first before we look into the details. Background: output stage of DC to DC converter usually consists of diode rectifier and output filter. Right? The focus for this chapter is on the diode rectifier, and typically we use Schottky. The reason being, Schottky is fast, right? It can handle the high switching frequency that DC to DC converters typically utilizing, right? Rather than PN junction diode. And this diode rectifier in DC to DC converters typically functions as a functions to rectify input pulses into the output voltage. So before the diode, the voltage shaped like a square wave, but then or AC square wave, and then after the diode, it becomes a DC square wave, right? Just one polarity square wave instead of fluctuating between plus and minus square waves. And then it also provides a freewheeling path. For example, in a buck converter, that's a good example where the diode that is being used there in the middle, right? That is being used for freewheeling the inductor energy. So the inductor is can discharge this energy through this diode, right? So those are the two different or basic functions of a diode used in DC to DC converter. Number one is to rectify input pulses into the output stage, and number two is to provide freewheeling path for magnetic energy to flow to the load, right? And then we have also output filter, and this is going to be covered in EE411 next year. There is actually a chapter, pick chapter on output filter. For DC to DC converter, the output filter as well as input filter, there's some interesting or unique characteristics that we need to watch out for, but that's not part of this class. Again, this is going to be covered in 527. Here's an example of flyback, right? You can see there's a flyback converter, and there's a diode right there, and this diode functions to rectify the input pulse into the output, right? And then we have another rectifier diodes right there from forward converter, right? That's a forward converter, right? The input is pulsating, but then the output requires DC, so you need to rectify the voltage from the secondary side of the transformer into DC, right? And then you filter it, and then you get a better DC that way, right? So you can see the critical functions of these diodes. And then we have, this is half bridge, right? You can tell from the two switches right there and the two diodes. And again, we have rectifiers, right? Diode rectifiers that would rectify the input pulses into DC, and then you filter that, right? So the voltage before the LC right there is to look something like this, right? Like that. So it's an AC pulse waveform, square wave waveform, I should say. And then, oh, actually, that's not it. That's actually from here. Sorry about that. That's from here. Right, so that voltage on the secondary side of the transformer is an AC voltage, and then you rectify it so that here, right, the output of that the diode network right there, diodes D1 and D2, will turn it into DC, like that, right? Oops, you get the idea, right? And then we introduce the filter, right there, LC filter. That would make it more DC, right? So that after the filter on the output, it will look like, hopefully it will look like that, right? It's more DC, like that. Okay, so that's kind of the process that we have for these kind of converters. Same thing with a full push-pull, flyback, forward, right? The kind of process. So again, the point here is I want to show you the critical role that these diodes have for the converter, right? They rectify the pulses as well as they serve as a freewheeling diode, for example, in a buck converter. Now, reason why I want to show those to you, because then we need to now consider non-ideality of these diodes, right? These diodes are not ideal, right? So therefore, when it's doing this, when it's performing these functions, right, we're going to have some losses from these diodes, and we'll talk more about the loss equations in diodes. But yeah, keep in mind that any diode that you'll be using for DC to DC converter, including Schottky's, will have a forward voltage drop, right? And in electronics class, you always use 0.7 volt for diode drop. That's just being used for convenience, right? And as you know, diode will have different voltages, right, for different currents, right? For Schottky's, the voltage drop is between 0.15 to 0.7 roughly, right? compared to a standard diode that goes from 0.7 to 1.7 voltage drop, depending on the currents. Reverse recovery time for Schottky, the reason why it's being used because it's fast, right? In a range of tens to hundreds of nanoseconds, right? And therefore it's useful for high frequency applications. Right? So here's the IV characteristics of the diode, right? Here's the PN junction, right? Notice that the current here is in milliamps, and the forward drop is in volts. So this shows you how much forward drop you get for a given current, right? That goes through this diode. So for example, I think that's 3 different temperatures. Yes, it is. Number 2. So let's look at number 2 as an example. Let's say that the diode is carrying, what is that? 2, 4, 6, 8, yeah. So 1.2 amps, let's just say. So this is 1.2 amps, right? Oh, 1.2 volts, sorry. Let's look at amperage, not voltage. My bad. So let's say that the diode is carrying, what is this point right there? 300, 400, no. 350, right? So 350 milliamps, let's just say, right? So 0.35 amps. So when the diode is carrying 3.5 amps, you can see that the drop across that diode is, if you draw a straight line across, right, and then down on curve number 2, then you can see that it's going to have a forward drop of about 1.2, right? 1.2 volts. Right, that's pretty significant, isn't it? So this diode is very lossy, as you can see, because when you have current and voltage together, right? They get married and they have a child called power, and the child, it's V times I, right? This power is V times I. So you can see the loss coming from this diode. Even at very tiny current, you get quite significant loss, right? Relatively speaking, of course. And then compare that, for example, with this diode, right? This is, what is this? This must be Schottky. Looks like I'm looking at the part number. And then this one is, there's no part number, so I don't know what that is. Oh, right here. Schottky, yeah, Schottky on the left, and then SBR on the right. Okay. So here's Schottky's IV characteristics. And let's do, wow, this is already amps, as you can see. Right, so it's not milliamps anymore, like the PN junction, that's amps. And what current do we have there? 0.35 amps. I don't know if we can actually read 0.35 amps from here. I don't think so. So the lowest is 1 amp. So you can see that, let's say that we draw 10 times, right? 10 times as much as this current, so 3.5 amps. 3.5 amps, that's 2, 3, let's say around here, right? That's the line, straight across at 25 degrees Celsius. That's the last plot right here, right? So that's gonna give you a drop of about less than 0.7 volts, right? Right here, right? So 10 times as much as the current, 3.5 amps, is only dropping around 0.7 volts, right? Compared to PN junction that I showed earlier with 1.2 volts drop with only 0.35 amps. That's a big difference, right, in terms of power loss. Let's look at SBR. SBR is another type of diode that is fast and as well as efficient for DC to DC converters. That's the 25 degree. What is the 25? Must be this one. Okay, that's the 25. And 3.5, right? 2, 3. So let's say around. It's hard to. Everything's kind of merging. So it's about right here, right? For 3.5 amps. So that's a drop of about 0.4. So you can see that if you pick this MOSFET, that's going to be more efficient than this MOSFET at MOSFET diode. If you use this diode, SBR diode right here, will be more efficient than this diode right here on the left. If the current is 3.5 amps at 25 degrees Celsius operating temperature, right? So you can see the drop that you get from Schottky's as well as SPR diodes, right? They're relatively lower than PN junction diodes. That's more reasons why you want to use Schottky's or SBR or DC to DC converters. Okay. Any questions on this? And typically these curves are available in the data sheet, so you can always get these curves from any manufacturer's data sheet for the diodes. Any questions? All right. So now it's good that with the technology that we have today for diodes, you can have two different options. Either you use Schottky's or SBR, right? For DC to DC converters. All right. Okay. Let's look at. We'll go back to this issue with voltage drop later, right? Keep in mind we have about 0.7, up to 1 volts drop. Same thing here, right? Around 1 volt or lower, right, for the drops across these diodes. But before we look into the problems that these can cause, these drops, let's look at how we calculate losses on these diodes, right? Since it is a very critical, one of the critical components in DC to DC converters, it will be good to introduce to you calculation on different losses on the diodes. Okay, so diode loss consists of forward loss, reverse loss, and switching loss. Just like the MOSFET that we covered in the beginning of this quarter, right? Has forward loss, reverse loss, and switching loss. Forward loss is approximated by losses from both DC and AC components, right? So we'll look into that more. Reverse loss considers reverse voltage and reverse current. And finally, switching loss consists of turn on and turn off loss, just like our MOSFETs. And turn off is probably the most difficult one to calculate or to approximate. I remember this fresh from my experience a long time ago, 2006 maybe, when I worked for the company who made this diode. I think I told you the story before, right? The company who studied this SBR diode is called APD Semiconductor, who then got bought by Diodes Inc. So I worked for this startup company called APD Semiconductor back in 2006. And it was a small group, right? Only 3 engineers, and we do a fail test on this diode, which was a fun test to actually do in the lab. And yeah, so that's the company, APD Semiconductor, and then got bought by Diodes Inc. And I remember that one of my assignments is to look at or calculate losses on this diode. So I remember, one of the most painful equations to look at for diode loss is the turn-off loss. You'll see. Okay. Let's start from the forward loss. Forward loss is pretty straightforward. No pun intended there. Forward loss is relatively simpler to calculate compared to the other losses. Here you have two different components of the forward loss. You have the DC component and the AC component, right? So you have to consider both the DC component of the loss as well as the AC component of the loss, right? The DC component looks at the DC components of the current and voltages, current and voltage, I should say, current and voltage of the diode when it's conducting, whereas the AC component of the loss looks at the AC component of the current and the R of D right there. That's the dynamic resistance of right here, dynamic resistance of the diode, right? And VF and IF, that's something that you already know from EE411. IF, especially IF, sorry. IF, that's something that you were able, that we look at in EE411 when we look at average current through the diode, right? So you should know how to calculate this from EE411. VF, that's a number that you get from the IV curve, right? So once you calculate IF, then you go back to this curve and determine what voltage drop is, right, per given IF. So you go from the y-axis, you calculate IF from EE411, and then determine the drop for that given IF, right? And then you get the first part of the equation done, right? And then the second part, which I don't usually include in the first pass of a loss estimation, usually I just, when I do first pass approximation of loss in DC to DC converter, I typically include just the first part right there. But once I finish with the first pass of the estimation of loss, typically efficiency estimation, right? Then the second phase of not calculating, but estimating efficiency more accurately is by including the second loss right there, right? So as I said earlier, in the second term right there, you have the AC component of the forward current of the diode multiplied by, so square it first, I square RMS times R of D. R of D is again dynamic resistance. How do you get R of D? It's not given in the other sheet directly, but you get it from the IV curve right here. So using the IV curve, right? And you know what? I'm just gonna draw the curve right here. So let's say that this is the IV characteristics, right, of our diode. Then because we have remember it's IF AC RMS times RD square. This is an AC current, right? So it has peak to peak value. So let's say that this current has a delta I diode of whatever it is, right? Let's say from 1 amp to 2 amps, let's just say. That's the ripple. Basically, that's the ripple current through the diode. So let's say that's 1 amp right there. And let's say this is your 2 amps right there, right, on the curve. And then from here, right, you get 2 points on the voltage. So you get, let's say this is voltage 1, voltage 2, right? And then from here, I get delta I, right? And then from the voltage, I get delta V, right? So then RD is approximately equal to delta V over delta I. Okay. So this is something that I don't have in the notes yet. So, but if you want to draw this in your book, go ahead. So that's how we approximate dynamic resistance, right, by looking at the fluctuation in the current, basically ripple, right? Ripple current through this diode, and from there you can do the peak-to-peak ripple, minimum current on the diode, maximum current on the diode, and you get the 2 points corresponding to this curve, right, the IV curve. And then from those 2 points, you get these voltages, and from those 2 voltages, you get delta V, and then from the min and max of the current, you get delta I, and then from there you get your dynamic resistance by dividing delta V with delta I. Any question on this? Okay, so that's how you get R of D right there. Here's an example, right? So you see you get this fluctuation, right? When the diode is on, right? You don't care about this one because that's when the diode is off, right? Remember, this is forward drop. So you only care about when the diode is conducting. So the fluctuations on the current is not 0 to I max, but rather is I min to I max, only when the diode is conducting, right? So that's what you look at the curve, right? You look at the curve for I min and you get V1, and you look at the curve for I max and you get V2, right? That would give you delta I and delta V for the dynamic resistance. Anyhow, for most of our DC to DC converters, the diode current looks like this, right? The trapezoidal waveform with the ramp down slope, right? That corresponds to the discharging path of the inductor, right? So that's why it looks something like this. You probably remember from EE410. And from there, in EE410, we have the table to find the average value, right? Or actually, we derive this equation for average value of the current, right, through the diode. For non-isolated is I out average. This is for a buck. Okay, this is only for a buck converter. No, actually, no. This is true for buck boost and buck boost, right? It's the same equation. No, I take it back. I'm sorry. This is only true for a buck. You know why I know this is only for buck?
Because IO is the inductor,
Yes.
or not the inductor.
Yeah, exactly. Right there. So that's our IL average. Very good. Still remember. So yeah, this is only true for a buck converter. For other converters, buck boost and boost, the equation should be IF average is equal to IL average times 1 minus D, right? Right. So, but this is an example for a buck converter. So you have the DC component or the average current through the diode, calculate it that way, and then the AC or RMS, total RMS of that current. Right, that's in one of the tables, right? I think in chapter 2 in EE410 book, we have that table that gives you average value and RMS value of commonly found waveforms in DC in power electronics, right? And for this waveform, you can see the total RMS equation is given in this equation right there, right? But what we are looking for is not total RMS. What we are looking for is AC only. See that subscript AC? So how do you get the AC component only? Again, you learn it from EE410 that if you have the DC component of the current and you have the total RMS of the current, then the AC component can be found by using the geometric sum, right? So, and then solve for the AC component only. So that's how you get or calculate the AC component of the forward current of the diode. Any questions on this? So not bad, right? Calculating forward loss is not that bad. Okay. Reverse loss. So reverse loss occurs when the diode is in the fully off or non-conducting condition. So you have to know the reverse voltage. That's what you learn in EE410 as well. Right? For example, in a buck converter, what is the peak inverse voltage of the diode in a buck converter, right? That's the same as reverse voltage that you need for calculating the loss, right? So PIV, what is the peak inverse voltage of the diode in a buck when it's off? Well, you can picture a buck converter in your head. So diode is off when the switch is on, right? So therefore, peak inverse voltage across that diode in a buck converter should be equal to V in, right? So for a buck converter, this is equal to V in, right? For a buck. Right? So that's what you put in there. So it's not bad, right? Finding the PIV there. IR is then determined from IR versus VR plot. So you have to estimate IR from the plot that is provided by the manufacturer's data sheet, right? So there's a plot that gives you reverse current as a function of reverse voltage, right? So once you determine reverse voltage, right, from let's say EE410, right, then you can calculate, or not calculate, but measure or estimate IR from this curve right here. So let's say it's 25 degrees Celsius and V in for a buck is 60, let's say. So that 60 is right here. And then you find a corresponding reverse current for 60 volt reverse voltage, which happens to be about what, right here? It's tiny, right? 0.000234, 0.0004, right? Looks like for 60 volts, right? It's tiny, right? But if you want to be very accurate in terms of finding losses, then you do this, right? And for me, if it's again the first pass of efficiency estimation, I don't usually include reverse loss because it's tiny. But for the second, what do you call it? Yeah, the second pass of the efficiency estimation, I start including all of the losses, including this one right here. Okay, and then the duty cycle, don't forget, right? It's not 1 minus D, right? It's duty cycle because typically the diode is off when the switch is on, right? So therefore it's D, not 1 minus D, because it happens when the switch is on. Any question on this? So far so good, right? Not bad. This next one is bad. The switching loss. Even turn on, it's not that straightforward, but the turn off is the worst. All right, so how do you estimate turn on switching loss for a diode? The switching behavior at turn on is characterized by a low value of peak forward voltage, VFP, and forward recovery time, VFR. Just like the reverse recovery time, when the diode is turning on, it also has forward recovery time. It takes time before this diode current settles into its steady state value. Right? Both VFP and TFR are normally plotted against the slope of the current through the diode, dIdt, in the datasheet. Whereas dIdt itself is also available in the datasheet for a given set of conditions. Right? So it's not as straightforward as the previous two losses, but it's not as bad as the turn-off, as you will see soon. So here is, let's say, here's the equation first. Right? So the equation involves VFP, VF, VFR, IF, and F, right? So one value that I know is frequency, that's the switching frequency. And then IF, that's the same IF as you have before, that's the DC current, right? DC current when the diode is already settles into its steady state value, meaning it's conducting fully, then that's IF right there, right? That's the DC current through the diode. VF, we already know this, that's a forward drop across the diode given IF, right? So these two are related, and you already know how to get VF from IF. The one thing that we don't know yet is those three, right? I believe we don't know what VFP is, or actually just two. We don't know what VFP and TFR are, right? So how do we do that? So yeah, unfortunately, you have to kind of look. If you want to be more accurate, you use the scope, right, to actually capture current through the diode waveform, such as this one right here, right? Same thing with the voltage across the diode. You capture it through a scope. Or if you want to estimate, you can just use the value that is given by the datasheet. But keep in mind that this is only true for certain condition, right? So you can see that, for example, this TFR that's given in the datasheet is equal to 500 nanoseconds, but that's only true under this condition right here. IF is 8 amps, VFDT 64 amps per microseconds, right? So that's only true for that. But if you feel like, okay, I'm just gonna do a rough approximation, you go ahead and use this value for TFR. Same thing for VFP right there, right? It's 10 volts, but again, that's only true under this condition, the same condition as the previous one, as the TFR. Again, it's okay for rough estimation, but if you like to get a more accurate measurements of the loss, again, you capture the waveforms, right? Current as the diode is turning on, voltage as the diode is turning on as well. And once you get those waveforms, then you can measure the slope as the diode is turning on, right? And from there, you use these two different curves right here, right? This one and that one, to get the more accurate values for VFP and TFR. See that? VFP and TFR, which is a function of the slope. See that? Slope. Does that make sense, hopefully? Any question on this? So that's how you calculate or estimate the turn-on loss of the diode.
Sorry, Professor. which slope do we know what to use then? Is it just because there's multiple slopes for the curve, right?
Yes, very good question. So initial slope, just initial slope right there.
Oh, okay, thank you.
That's kind of like a linear curve right at the beginning. So use that one.
Wait, and that was given by the table, right? The table above, like the amps per second.
No, this is not given. This is a curve that you have to measure yourself, that you capture yourself on the scope. The one that's given by the table, it's only true under a certain condition, right? It's only true when IF is 8 amps, right? Right there. And it's only true, the same thing for peak forward voltage when IF is equal to 8 amps, right? The curve that you have here might be at different amperage, right? This IF would be different amperage.
Right, so different slope.
It's going to be different slope, yes. But again, if you're just going to do a rough estimation, go ahead and use the one from the table. Right? More accurate way, then more work, right? You have to do more work. Go to the lab and capture these waveforms and then calculate or estimate that slope, and then go to these curves which are given in the manufacturer's data sheet and get VFP and TFR from these curves, right, as a function of the slope, as you can see. Any questions? Good.
What are we using the slopes for again, with reference to the equation?
To get VFP and TFR, right there. VFP and TFR, you need those.
Okay, thank you.
Right, yeah. So again, let me erase it because it's getting crowded. All right. So for this equation, right, what I'm saying is that there are two ways to get VFP and TFR, right? Using rough estimation, just use the table that is provided by the manufacturer's data sheet, right? That would be the easiest way. Just use those values, but those are only true for certain condition. That's why it's not going to be as accurate. If you want to get it, if you want to get more accurate values, then you need to capture the waveforms yourself, right? Current through the diode as it's turning on, voltage across the diode as it's turning on, and then you again estimate the slope, right? And then from there you get, from these two curves, you get your VFP and TFR based on the slope. Is that clear, Nick? I want to make sure that that's clear.
So is VFP equal to the slope?
No. VFP is a function of the slope.
Okay, got it.
Right here. So let's say if the slope is 80 amps per microsecond, right there. Right? Then now that would give you 9 volts for the peak, and so on and so forth. Same thing with TFR. Depending on the slope, that would give you the TFR, right? For 80 amps per microsecond, right there. Well, that's actually a pretty good point to use. You can see that's going to give you 150 nanoseconds for TFR. Was that good, Nick?
Why would you get the slope and not just pull the value directly off the graph then?
What do you mean?
Just the slope
from the graph. Oh, from the graph here? From that graph?
Yeah. Oh, okay. I see. That becomes the independent variable. I see.
Yeah. Or, I mean, that's a good point too. Maybe you don't really need this, right? Looks like. Because if you know the slope, then you can know VFP and TFR, right? You just need this, the one on the left, to get VFP and TFR. That's a good point.
Okay.
Yeah.
Thank you. That makes sense.
Okay, good. Yeah, good point though. All right. This last one, oh man. Turn-off switching loss. Turn-off loss constitutes appreciable switching loss. And it is the worst, right? As you know, turn-off loss is the worst out of the 4 losses, right? Forward loss. Actually, no, it's probably comparable to forward loss. And then there's a reverse loss. Reverse loss, not much. And then we have the turn-on loss. Turn-on loss usually not much. And then the turn-off loss is quite big, right? Especially for lossy diode. And you ready? I'm not. The equation is long right here. I just remember the pain right there. Right, so good luck if you ever need to do this. It's a long equation, and it's all of these are just approximation as well. And you're gonna have to capture the waveforms on the scope so that you know how to fill in those parameters in the equation right there. Because we have, for example, ID naught, dID dt, right, TRRA, and so on, so KRR, right, and so on and so forth. Oh, TRRB, right? If you are wondering what those are, then you'll see those from here, right there, right? So you actually have to measure or capture using scope, right, the current through the diode as it's turning off, right? So here's current through the diode as it's turning off, and there's the voltage across the diode as it's turning off, right? You overlay the two, and you can see the different values that you need to enter into this equation. I'm going to leave it like that, okay? So it is. It takes time to do this, okay? As you can already tell, it's the most painful one to calculate. But that's basically it for turn-off loss. Okay? Very long equation, multiple parameters you have to measure from the waveforms that you captured through the scope, and measure these values and then plug in those values into the equation, and that will be it. I mean, it sounds like it's not that bad, but trust me, it's bad. Okay, any questions on those? So now we're done with the different equations to calculate losses on diodes. Any questions? If not, let's see the problem the technical issues that we can encounter when you have forward drop right across this diode. If you think about buck converter, for example, or actually flyback is probably a good one. Right, you have a MOSFET on the primary side, and then you have this diode, right, on the output, right there. And here's our output voltage, and here's our secondary side voltage from the transformer, and here's our diode right there. Let's call this drop voltage VF, right? By looking at this topology, right, hopefully it becomes clear the reason why forward drop across the diode becomes significant, because look at how the diode is connected to the load, right? If you do KVL, that's actually in the same loop, right? So this becomes a problem. Imagine if the output voltage gets low to the point that the output voltage level is close to the forward drop across the diode. That would be a problem, right? You're taking away voltage from the secondary side of the transformer that's going to be comparable to the output voltage. That's going to be a problem, especially in terms of efficiency, because the same current flows, right? DC current, right? I'm ignoring the AC current, just the DC current. You can see that they have the same current flowing through each. And so if the forward drop across the diode is comparable to the voltage output, then we have a problem in terms of efficiency, right? Imagine the loss is going to be big, right? Almost as big as the output wattage. Go ahead and do VI, V times I. If the two are comparable, then V times I here, which is what we want, is going to be almost the same as V times I across the diode. That's not good, right? That's efficiency hit right there, big time. So here, in this section right here, basically what let's look at, a lot of words here. What I'm trying to explain is that Yeah, these diodes are great, right, when it comes to doing the job as rectifying the pulses as well as freewheeling the energy. But we got to watch out for this forward drop across this diode. We want to make sure that this forward drop is not as big as or comparable to the output voltage. Right? That's when we run into the problem. Right? And if you look at how technology is heading these days, right? That's what we are seeing nowadays, is that our load output voltage right here, right, is typically, or not typically, but it's getting lower and lower. That's becoming a trend, that the output voltage now is getting lower and lower. And that poses a problem, right, with this drop across the diode. Right? So low voltage supplies are becoming more common nowadays, right? Because the loads are requiring low voltage nowadays, right? Such as 1.5 volt supply used to terminate high-speed data buses that requires low voltage, right? So now it's very common to have, low voltage load. And remember the forward drops across the Schottky's or SBR, let's say around 0.4 to 1 volts, right? Or 0.4 to 0.7. Well, that is all fine if the output voltage is, let's say, 15 volts, right? If the output voltage is 15 volt, 0.4, 0.7, that's only a small fraction of 15 volts. But what if the output voltage is 1 volt? That's a problem, right? If the output voltage is 1 volt, then 0.5 drop across this diode will represent, 50%, portion of the output voltage, right? That is not good in terms of efficiency, right? They both are seeing the same current, right? So hopefully that makes sense to you why it is that when the output voltage goes lower, we have problem using this diode, right? In more specifically in terms of the forward drop across this diode. It is small, right? It is small drop, but when the output voltage becomes even lower, then yeah, we got a problem. 3.3 volt systems have become the rule rather than the exception, right? Well, some components, most notably microprocessors, have dropped below 2 volts. Right? So a lot of microprocessors nowadays are running at 1.5 volts, right? 2.5 volts, right? Instead of 5 volts. Some predict that in the next 5 to 10 years, many devices will operate at less than 1 volt. Can you imagine if the load is 1 volt or less than 1 volt, right? Then the diode drop becomes a real problem, right? And that gets worse as the current goes up. And you could see that with load that is running at low voltage and high current, right? For processors, for example, right? Processors can run at very low voltage, let's say 1.5 volt, at hundreds of amps, let's say 200 amps, right? Can you imagine if your load is requiring this, right? How much, if you look at IV characteristic of the diode, right? And you measure 200 amps, it's probably gonna be big drop, right? If it's 200 amps, this is IV characteristic of the diode. If you use a diode, that 200 amps is going to be probably close to 1.5 volt, right? If not, maybe the same or even higher if you're not careful on selecting the diode, right? So it is a problem. And then increased popularity of battery-operated electronic systems will also demand low voltage systems, right? More compact system enclosures, denser board level designs, less power consumptions, right? These are all requiring low voltage operation, right? So that's why the trend, nowadays is for consumer electronics to go, lower and lower voltage, right? And in order to provide this low voltage, the power supply to supply the power, namely the DC to DC converters, will also have to be able to output low voltage, right? And then if we stick with our diodes into this DC to DC converter, then we're going to be having a problem, right, with efficiency. Does that make sense in terms of why diode can pose a problem at low voltage applications, low voltage and high current especially.
Yeah, that makes sense.
Okay, good. But why lower voltage? Mainly efficiency, right? And then all of those reasons I explained earlier. Battery life is a function of operating voltage. Right? The lower the voltage, the lower the operating voltage of the battery, the more efficient the battery is, the more battery life as well, right? And then, oh yeah, this is a good one, right? Lower voltage also requires less number of batteries being connected in series, right, to make it a more compact system, right? So rather than having 3, 4 cells, battery cells in series, you can just have 2 maybe in series, 2 cells, right, to make it more compact systems. But 2 cells of these batteries means low voltage, right? So if the rest of the circuit can handle low voltage, that'll be awesome, right? So that way you don't really need high voltage to be present in the circuit. So I talked about this already, the power consumption, impact of low voltage to output shortkeys, efficiency of the rectifier, or in this case diode, right? Diode rectifier degrades significantly with low voltage. The study shows that per given output power at 5-volt operating voltage, the efficiency was calculated to be 92 to 93%. That's at 5-volt output, right? If we reduce the output to 2 volts, then the efficiency for the same output power reduces to 80 to 85% efficient, right? And if it's 1 volt, even lower operating voltage, then the efficiency is becoming even worse to 75%, right? And here's another example I got from one of the articles that I read a long time ago. For a step-down regulator with 3.3 volt output and 12 volt battery input, the 0.4 forward voltage of a Schottky represents a typical efficiency penalty of 12%. That's big, right? 12%, that means you're starting with 88% efficient for the entire DC to DC converter, right? The 12% comes only from the diode. And that is not good, right? So you got to do something different here, right? So that's why we have what we call synchronous rectifier, right? Or synchronous technique, right? Synchronous method, where we use MOSFET instead of a diode. Right? So we replace the diode with a MOSFET. Why? Well, mainly because it's more efficient, right? MOSFET has less forward drop compared to the diode for the same amount of current, right? Reason being, MOSFET has small RDS on, right there. And then that would cause the drop across the MOSFET to be much lower than a diode, a Schottky diode, right? So that is what a synchronous method is. You're replacing the diode with a MOSFET. And here is an example of the benefits that you get from synchronous rectifier, meaning replacing the diode with a MOSFET. You'll be doing this experiment today, by the way, and Thursday for some of you. Hopefully you get the same kind of curves for the 2 different cases. So with synchronous rectifier or with MOSFET, you can see that the efficiency is higher than the one without the one that has the diode, right? And this is done for this part from Maxim, right? And these conditions right there. And this plot, I forgot to mention, it's being plotted, or these points are being plotted based on output voltage, right? And they measure the efficiency based on the output voltage, right? So you can see that on the x-axis, you have this output voltage that is being increased, right, from 0.5 out output voltage to 5 volts, right? And you can see the efficiency curve, right, for the one with the MOSFET instead of diode is always higher than the one with diode. And notice the efficiency gain, right? Go ahead and compare per given output voltage. For example, if you look at 4 volts, look at the difference in terms of the gain in efficiency right there. Right, that's that much, right? That's that much difference right there in terms of efficiency. At 5 volt, that's going to be that much different, right? But look at the gain that you get in terms of efficiency at very low voltage, let's say 0.5. Look at the gain. Look at it. Look. Right, the efficiency gain is big, right? At low voltage. What is that? 50, let's say 50 to about 65. That's 15%, right? Even more. So roughly 15%, maybe 20% gain in efficiency at lower voltage. So you gotta, take advantage of this, right? So if you're in the future, if you're designing DC to DC converter that outputs very low voltage, such as 0.5 or 1, you might want to use synchronous rectifier because you can see the gain in terms of efficiency by using or by replacing the diode with a MOSFET. That's what I want you to see right there. Is that the efficiency gain is the best, right, at lower output voltage than higher output voltage. Okay. And here's more examples. What do I have here? Output current versus efficiency, 12 volt input at 1.5 output, and the next one is 12 volt input at 2.5 volt output. So the one on the right is higher output voltage than the one on the left. And this is from Texas Instruments. You can see the plots that have the blue dots and the red dots, right? The blue dots is for non-synchronous, the red dots for synchronous. So you can see the, what do you call it, the benefit of synchronous, right? From the lower voltage out. The higher voltage, you can see, it's not much, right? That the synchronous can only give us, better efficiency at larger current, right? And only that much range. But when you lower the output voltage to 1.5, from 2.5 to 1.5, you can see the benefit gets bigger, right? In terms of the range. Okay. Imagine if they did another experiment with 1 volt output, 0.5 output. Right? That's something that you'll be doing today in the lab. All right. That's another example here. This is just showing you, I believe, different type of Schottkys, different type of MOSFET. So this is a good example to show as well, because the gain that you get in terms of efficiency, the red solid line and the green solid line, those are synchronous, but they are using different type of MOSFETs. So be careful on which type of MOSFET you are using as well, because that would determine how much the gain in efficiency you're getting, right, by using synchronous. So you got to watch out for the type. You got to watch out on how to select MOSFET. We'll talk about it toward the end of the class today, if we have the time. Otherwise, we'll do it on Thursday. Okay, I got more examples here to show you the benefits of synchronous rectifier. Right? Let's look at 2 different cases here. Let's say I have a 30-watt buck converter. Okay, and then case number 1 uses Schottkys with 0.5 volt diode forward drop, and then case number 2, MOSFET with RDS on off 10 milliohms. And assume 25% duty cycle and 10 amps pulse current. And the only conduction losses considered here would be, for the top MOSFET, would be the conduction loss. So imagine I have a buck converter, right? Here's case number 1, and here's case number 2. Okay. And the duty cycle is 25%, 10 amps pulse. So if I draw the current through the MOSFET, through S1 right there. So the current through S1 is going to be 25% duty cycle, something like this, right? With a peak value of 10 amps right there, right? So that's what I'm saying. And then the top MOSFET, we're going to assume has a constant loss of, what is it, 0.5 watts. So 0.5 watts in both cases. Right? So we're going to focus on the calculation of loss on that diode and on that switch S2, synchronous switch S2. Right? All right, case number 1 with diode. So P diode loss on this diode, you can see that I'm ignoring the AC component, right? Remember earlier when we talked about forward loss of the diode, there's actually the second term, which is the AC component. I'm going to ignore that. I'm just going to do the DC component only. All right, so you can see that the loss on this diode, D1, is VF times IF, right? And VF is, what is it, 0.5 right there, right? 0.5. And IF, that's going to be the average current through the diode, right? If this is the current through the MOSFET, S1, then through the diode would be the complement of that, right? Would be this, right? That's going to be through D1 or through S2, right? Okay, so that's why when I calculate average current through the diode, that's going to be the average of this current right there, right? The second one right here. So that's going to be the peak, which is 10 amps, times the duty cycle of this diode, which is 1 minus 0.25. Right? So that's going to give us 3.75 watts of loss. This loss represents total watts is 30 watts right there, total output power, I should say. The total output power is 30 watts. And 3.75 watts represents 12.5% of the output power, right? Whereas, before I do that, and then from there I could calculate efficiency, right? Efficiency of the converter is equal to P out over P in, P out over P in, and P in is can be calculated from P out plus P loss. Right, so that's what P in equal to, right? The output power plus the loss in the converter. And in our case, we have our loss is 3.75 watts plus 0.5 watts, right? So the 3.5 is from the diode that we just calculated. 0.5 is for the top MOSFET that we assume to be constant loss, right? 0.5. So if you do that, then you get 87.59% efficiency with case number 1. Okay, any question on this? Case number 2, I'm going to replace that diode with a Schottky's or a Schottky's MOSFET, not Schottky's, with a MOSFET. And now the equation for finding the loss will be different. Okay. So now imagine if I replace this diode with a MOSFET, then the equation to find the loss for that MOSFET will not be the same as this anymore, right? That's only for diode. So it has to be the loss equation for MOSFET, which is I square RMS times RDS on, right? And we learned from 410 that if you have a pulse current, how do you find the RMS value of that current? That's going to be the peak times square root of 1 minus D, right? So that's one of the entries in the tables in the EE411 book. Then you square it. I square RMS times RDS on, and RDS on is given to be 10 milliohms, right? So that's what I have right here. That gives me 0.75 watts loss on that MOSFET, right? So this 0.75 watts represents 0.75 divided by 30 watts. That's 2.5% of the output power. And if I calculate the efficiency of this, you get 96% efficient compared to, what was it before? 87%, right? So almost what, maybe 9% gain. Yeah, almost 9%, right? So 96 minus 87.59, that's roughly, that's 8.41% or roughly 8% efficiency improvement by replacing the diode with that MOSFET. Okay, so that's pretty good gain, huh? Any questions? Now I can also look at this benefit from a different angle. For example, if instead we assume that the efficiency of the 30-watt buck with synchronous rectifier is 89%, right? So let's draw this. So let's have again two different cases, right? This is with synchronous and synchronous buck, and the next one is non-synchronous buck, right? So let's say that the efficiency of the first one with synchronous rectifier is 89%, right? Let's just say, and then for case number one is actually the non-synchronous case right there. That's case number one. The non-synchronous buck, since we are starting with 89% from synchronous buck, and the non-synchronous buck is 8.41 less, so therefore I subtract 8.41 from 89%. That gives you 80.59%, right? And that will be the efficiency of the non-synchronous buck, 80.59%. And by knowing so, since I know the output power is 30 watts, right? These are both 30 watts. Therefore, I could get P in, right? So P in, as you know, efficiency is P out over P in. So therefore, P in is equal to P out over efficiency, right? And so that's what I did right here. P out over efficiency. That gives you 37.23 at the input of case number one right here. So 37.23 watts here. All right. So if you have 37 watts at the input and 30 watts at the output, therefore the loss in the converter is the difference between the two, right? 7.23 watts. Right. So that's this right here. So that 7.23 watts, that's what the packaging of this, or the converter module that you're designing, will have to dissipate, right? So that's how much power dissipation is on that converter. Compared to the case number two right here, right? Now, since we know the efficiency is 89%, output is 30 watts, so therefore input power is 33.71. So now the input here is 33.71. Again, if I know input power, I know output power, then I would know the loss, right? Which is the difference between the two. So that's going to be 3.71 watts. So the converter module for case number two will dissipate 3.71 watts, right? A little bit over half of the first case, right? Okay, so that's another angle of showing the benefit of synchronous rectifier, is that power dissipated in the module is less, right, or improved because of the synchronous rectification, right? Any question on this? All right, and then oh yeah, this last one hopefully. Yeah, last calculation. All right. So you might say 8% improvement. That's not much, right? Right here, 8.4 to be exact. You may say 8% is not much. Well, maybe, but if you look at the 8% efficiency improvement from how much output power the converter can deliver, then hopefully I can change your mind about saying that 8% is not much, right? So let's look at how much output power can a 8% improvement deliver, right? So let's see by using this example. Consider two buck converters having the same package loss of 2.5 watts, right? So now I'm limiting the power dissipated in this converter, right? So here's the non-synchronous buck and here's the synchronous buck, right? And both of them has the same package loss, 2.5 watts, 2.5 watts, right? And then for case number one, 80% efficiency, right? And case number two is 8% more, right? So that's 88%, right? If you say, oh, that's only 8% more, well, let's see how much gain you get on the output power by increasing the efficiency by 8%, right? 80% to 88%, right? And yeah, so output power that can be achieved in each case. So case number one, first of all, efficiency is P out over P in. So P out stays as P out, and then P in is P out plus P loss in the package, right? So now I know that the efficiency for case number one, the equation would be P out, efficiency equal to P out divided by P out plus P loss in the packet in the module. That's 2.5, right? That's going to give you 0.8, right? That's 0.8 efficiency right there, right? So that's for case number one. For case number two is the same equation, P out over P out plus 2.5, except the efficiency now is increased by 8%, right? So 8% more, 0.88. Now the only one unknown from these equations is the P out, right? So we look at the first equation. The only unknown is P out. So by having this equation, I can solve for P out. And look at what P out you get on case number one. You get 10 watts. Look at the P out that you get from case number two by having 8% efficient more, 8 more efficient converter, right? From 0.8 to 0.88. You got P out of 18.33 watts. Now let's look at the number here, right? Because 8% may not mean much, but when you look at how much power it can deliver, it's actually means a lot, right? Because from 10 watts output power to 18.33 watts output power, that's an increase of 83.3%. So now it's not a small number anymore, right? Again, this is achieved, this 83.3% increase in output power is achieved by increasing the efficiency by 8%, right? So hopefully you see that just because it is increasing by 8%, it doesn't mean that the benefit that you're getting is small. Right? It's not. Right? If you look at it from different angle, like here, you can see that the gain that you get from output power is a lot, 83.3% to be exact from this example. All right. Any questions on this? No? All right. If not, that will be it for today's class. We only have 3 more minutes, unless you have any questions about the lecture today.
I had a question on application.
Yeah.
Last quarter, we were working on I think it was boost converters for our final project, and you mentioned that we can do synchronous converters rather than a diode, and you said it would apply to different cases. Is having lower output voltage usually when you apply that for buck and boost converters?
Yeah, especially in general, output power, right, instead of output voltage. The most benefit you get, because when you get a boost converter, the output is higher than the input, right?
Yeah.
So therefore, how do you get low output voltage? I think the more general way of saying the benefit of synchronous rectifier is that it becomes, it gives you the benefit in terms of efficiency when the output power is getting large, it's getting big. So if the output power is big, you remind me of something. So I was going to show you this though, which I forgot, and thank you for reminding me. I actually included these examples right here. So I captured the screen from different websites, and you can see this is from On Semiconductor. That's the chip number, NCV8852. Can you tell whether or not this is synchronous or non-synchronous? Anybody?
Non-synchronous? Because it has that diode?
Exactly. This is non-synchronous. What topology?
Buck? Because the output's the inductor?
Very good. Very good. So now we have a non-synchronous controller, right? And then look at the second one. What topology is this?
Looks like synchronous, but there's some snubber action or something going on.
Okay, what topology? Anybody
Isn't
know?
that boost?
Boost, or is it buck?
It looks like buck.
Yeah, it is a buck converter. right? So
Oh, I was looking at the wrong Vout. Never mind.
yes, yeah. So it's not a bug, but it is synchronous, right? And I like this the way they draw the schematic, because you can see the grounds, the way they draw the signal grounds different from the power ground. I don't know if you noticed that. And then they connect the two grounds, the signal ground and the power ground, with 0 ohms resistance. I like that. And then Nick, you ask about boost. So that's how do I get it up? Okay, right here. You see that? What
Yeah.
topology is this? Here's your input on the left. Here's the output on the right. Look at the inductor, location of the inductor. What topology
Looks
is
like
it?
a boost.
Boost.
It's a boost, right? And is it a synchronous or non-synchronous?
Synchronous.
Synchronous. Look at the output voltage. It's not low, 24 volts at 4.5 amps, right? But that's high power, right? That's maybe almost 100 watts, maybe, right? So output power is high. That's why they made these synchronous boost to make it more efficient. And look at the circuit right there. What do you call this circuit? Right there.
Snubber?
Snubber, yes, very good. All right, and I think one more thing, and then we can adjourn right there. So it's not only for non-isolated, but it's also for isolated converter. Oops. Can you tell me what topology is this?
Flyback, right?
Flyback, very good, very good. So you can see the diode of the flyback is replaced by a MOSFET right there, right? So keep in mind that we also have controllers that being used for isolated synchronous topology.